Okay, now back to our main storyline. We're still in part 1, theory and design. So we saw the objective function, we saw more specifically the data correcting term in this objective function, and the last video was about the annihilating term and how we modified the DSO operator. And now we're going to sample the FWIME objective function on a simple transmission experiment, and we're going to show you how we can convexify the conventional FWI objective function. We consider a transmission experiment where we place two vertical boreholes separated by 1 kilometer. In the left borehole, we place 100 sources every 10 meters. And in the right borehole, we place 100 receivers every 10 meters as well. Our seismic source contains energy ranging from 9 to 35 Hz. We model noise-free data with an acoustic isotropic engine and a 10-meter grid spacing. Finally, the true model is assumed to be homogeneous and is set to 2.5 kilometers per second. We sampled the FWIME objective function for a set of uniform velocity models ranging from 2 kilometers per second to 3 kilometers per second by increment of 0.05 kilometers per second using the full data bandwidth. We also conduct this sampling for 7 different epsilon values, where epsilon is the trade-off parameter discussed earlier. And finally, we sample the conventional FWI objective function. This plots the various FWIME objective functions as a function of the velocity model value. Each color corresponds to a different epsilon value. We begin by epsilon equals 0. As expected, the FWIME objective function is null and constant across all models. This confirms the claim that we made earlier. Indeed, as we increase the epsilon value, we can observe that the shape of the FWIME objective function changes. We can also observe that for a certain range of epsilon values, the objective function becomes free of local minima. Now, if we examine the highest epsilon value, here epsilon 6, we can see that the FWIME objective function, which is plotted in black, is pointwise identical to the conventional FWI objective function, here plotted in the dashed yellow curve. Again, this illustrates our previous claim. Let's examine the curve computed for epsilon 2 more carefully. For this epsilon value, the FWIME objective function is now free of local minima, at least for the range of velocity values we sampled. However, by looking at the shape of the curve, we did widen the basin of attraction centered around the global minimum, but probably at a price of a slower convergence rate. Even though it can be dangerous to draw any conclusion from simple numerical examples, this illustrates the philosophy behind our method. That is, FWIME should be used to avoid falling into local minima that more conventional methods are sensitive to. Then, it should be stopped when an accurate enough model has been found to feed it to the more standard methods, as we explained at the beginning of the video. Okay, so let's recap one more time everything we've learned about the FWIME objective function so far. This is our FWIME objective function, and as we saw, it is composed of two terms. First, the data fitting, which we saw was a modified version of the FWI objective function. Then, the annihilating term. This term was designed to resemble a certain type of objective function from an MVA technique. Then, we introduced the data correcting term, whose goal is to fit the observed data. It is the application of the extended Born demigration operator B-tilde, which is an enhanced version of the conventional demigration operator, onto an extended perturbation P-tilde star. In FWIME, the role of P-tilde star is twofold. First, it helps us match the observed data with great accuracy. And it also brings kinematic information that we can leverage in the annihilating term or the MVA term. Our annihilator D is a modified version of the DSO operator. It penalizes the presence of any energy in P-tilde star while still bringing nice convergence properties inherent to a specific MVA technique we discussed earlier. Finally, our hyperparameter epsilon is responsible for balancing the two terms of our objective function. It is chosen and kept fixed throughout the inversion process. Low epsilon values will make FWIME listen more to the MVA term. And for high epsilon value, FWIME becomes FWI. Okay, so this concludes the part 1 of our presentation, Theory and Design. And in the next part, we're going to talk about optimization with our model space multiscale approach. We're first going to look at the FWIME gradients, then we're going to introduce our model space multiscale approach, and finally we're going to test that on some very simple numerical examples.